Hi everyone, welcome back. In today's video we're going to be looking at rates of change in the natural and social sciences. And all we're going to be doing is applying these concepts for derivatives that we have previously seen. And to start off on this example, we're going to be looking at this particular case where this says, if a ball is thrown vertically upward with a velocity of 80 feet per second, then its height after t seconds is s of t, which is equal to 80t minus 16t squared. And what we want to know is part A, what is the maximum height reached by the ball? And in order to establish what it is that we're looking at here, or let's say how to interpret this derivative-wise, well, we have to then identify what type of function we're given. This type of function that we're given, this s of t, this is a function that when graphed is a parabola. A parabola which will naturally open downward because we have a negative 16t squared. Now, because this is the case, when we're looking at a velocity, we're really looking at a rate of change. The rate of change is 80 feet per second. Now, as the velocity, or as this ball starts reaching its maximum height, look at its velocity here, or the slope of its tangent line. The slope of the tangent lines actually get to tell us what it is, or what this rate of change is that we are concerned about when we're looking at this. So we then want to find out what's the maximum height. Well, the maximum height is when, in this particular case, velocity is equal to 0. So what we then have to do is, if we have a position function like we do here, we can track its position. All we have to do is take the derivative. So when we take the derivative with respect to t, we're going to get 80 minus 16 times 2, it's going to be 32t. And we must set this equal to 0, that way we find when this velocity is equal to 0. Once we're able to find this, or once we're able to solve for this, we're going to get a t value. So 80 divided by 32 should get us 5/2, which means the time it takes to achieve its maximum height is 5/2 of a second, or 5/2 seconds, which means 2.5 seconds. And so what I want to do at this point in time is I want to find out what is that maximum height. So I'm going to use my initial equation to find what is that maximum height, knowing this time that it takes to reach it. So s, that's my height function, evaluated at 5/2, is equal to 80 multiplied by 5/2 minus 16 times 5/2 squared. Okay, that's looking pretty good. 80 divided by 2 will get us 40, then 40 times 5 will get us 200. So the first term is 200. The second term, the denominator is 2 squared, which is 4. 16 divided by 4 is just 4. So we get 4 times 5, which is 20. All right, looking pretty good. All right, so then we can keep going. All right, oops, my apologies here. It's 4 times 25. Sorry, I forgot to square the 5. So 4 times 25, that should get us 100. There we go. And 200 minus 100 will just be 100. So in this particular instance, and I'm just saying substitute. In this particular instance, we get that the maximum height reached by the ball, so the maximum height reached by the ball is 100 feet. And this is your first answer. Very nice. Second question, or the second part, then says, what is the velocity of the ball when it is 96 feet above the ground on its way up and on its way down? In order to answer this question, then we must substitute in the height that we're given. Since we're given the height of 96 feet, I now need to investigate at what time value is this height of 96 feet achieved. So again, 96 feet is equal to the equation that models the height of the ball at a certain time. So what I'm going to do here is I'm going to go ahead and start trying to solve for t. Well, the way to do this is that this is a quadratic, so I want to use that whole process of a quadratic equation to try to solve. So let's get everything onto one side. 16t squared. There we are, 16t squared minus 80t. There we are, plus 96. And I believe these are all factorable by 16, so let's factor out a GCF of 16. And we're going to be left with t squared. When we take 80 and divide out 16, we get 5t. And when we take 96 and divide out 16, we get 6. All this is equal to 0. 16 is a constant. If we divide by both sides, then we naturally just arrive at t squared minus 5t plus 6. And this can now be factored. Well, this factors into t minus 3 times t minus 2 is equal to 0. Which means we get two time values. We get t is equal to 3 or t is equal to 2. Now again, because this object, this ball, is traveling in a parabolic arc, as such, a height of 96 feet, say that this was 96 feet here, we can see that one way the ball is moving upward, reaches its maximum height, and then it's going to start going back down. And so there we see that the ball does attain that height of 96 feet at two different points. We now found the time values where that occurs. Now the question is asking, what is the velocity? In other words, we have to use the velocity function. The velocity function is the derivative of the position function. So the derivative we already know. We took that in the previous part. That's s prime of t, which is equal to 80 minus 32t. All we have to do is figure out what are these velocities. Okay, and I'm just going to outline this here. The velocity is the derivative of the position function. Perfect. So let's start subbing them in. So s prime at 3, well, in this case we're going to get 80 minus 32 times 3. And so when you do 80 minus 32 times 3, you should get negative 16. Okay, so s prime at 3 is negative 16. All right, that's great. Now we're going to look at the other one. S prime at 2. Oops. right. Whoops, my apologies, everybody. I have no idea what's going on there. There we go. Back at it. Okay, so we have S prime at 2, and this is going to be 80 minus 32 times 2. And this here is going to get us a positive value for 16. So this is going to be 80 minus 32 times 2. We just get 16. Awesome. Now, what does this mean? Well, this actually tells us that my velocity at time is equal to 3 seconds is negative 16. What does that mean? Well, at t is equal to 3 seconds, the ball's coming downward, which means it has a downward velocity. At t is equal to 2, the velocity is positive, which means that this ball is headed in an upward direction. So when we start analyzing this, we can now start summarizing what we found. So I'm going to say that the ball has a velocity of 16 feet per second on its way up, and negative 16 feet per second on its way down. And that's it. That's all there is to it for part A and part B. Again, we're just applying these derivatives and the concepts that we've been learning so far. Let's look at the next example down below. This example says that if a tank holds 5,000 gallons of water, which drains from the bottom of the tank in 40 minutes, then Torricelli's law, that's supposed to say then, there we go. Then Torricelli's law gives the volume V of water remaining in the tank after t minutes as V is equal to 5,000 multiplied by the quantity of 1 minus 1 over 40 times t quantity squared, where t is bounded between 0 and 40. And again, t here is going to be time, and that's in minutes. The problem already said that it takes 40 minutes to drain the whole tank, which means t is going to start at 0. That's when we start to count, and then 40 minutes later it's completely drained. So the question here is find the rate at which water is draining from the tank after, and we'll say 20 minutes. After 20 minutes. There we are. So again, what we're looking at here is that we want to find a rate. Remember, rates of change is that technical term for this derivative process that we've been developing in this chapter. So when we want to find that rate of change, again, we're talking about a derivative. So when I take my function v, where v has the variable t, volume, as a function of time, this is 1 minus 1 over 40 t, quantity squared. And we're going to take the derivative. In other words, we're going to apply the derivative with respect to t. So what do? Well, according to the chain rule and power rule, we're going to drop the exponent forward, multiply by the function, subtract 1 from the exponent, and then multiply by the derivative of the inside. The derivative of the inside, t, is being multiplied by the constant of negative 140. So the derivative of t will just be the constant that's multiplying by it, which is negative 1 over 40. Awesome. So again, I'm just going to highlight this just to say that we use the power and the chain rule here. All right, so that was the power and chain rule. Perfect. So let's go ahead and let's try to clean this up just a little bit more. That way we can start finalizing everything. So we take the 5,000 constant, we're going to multiply it by 2, but then we divide by negative 40. When that happens, we're going to be left with negative 250. So our v prime of t will be equal to negative 250. There we go. Multiplied by 1 minus 1 over 40 times t. And so this is now the derivative that we're looking at. And we now want to find what is the rate at which the water is draining from the tank after 20 minutes. We have to use this derivative, that way we can start analyzing that rate. Because if the original volume was gallons, when we took the derivative with respect to time, now we have gallons per minute. So the unit of measurement for this v prime is gallons per minute. And I'm just going to abbreviate that as GAL divided by MIN, gallons per minute. So let's go ahead and let's find 20 minutes. So let's find this rate of change for this gallons per minute at 20 minutes. Negative 250 multiplied by 1 minus 1 over 40 multiplied by 20. There we are. All right, so we can simplify this just a little bit more. Negative 250 multiplied by 1 minus, this is going to be 1/2. 1 minus 1/2 is 1/2. And now all we have to do is take half of 250, which means we'll get negative, because that's a negative value, we will get negative 125. Now remember that unit of measurement. So the water is draining at a rate of negative 125 gallons per minute at 20 minutes. And now we could then start analyzing. That's the halfway mark. As we get closer, or as time gets closer to 40, what's going to happen here is that this rate is going to be slowing down. Because again, you're letting the water out, which means the water pressure is going to lessen with the less amount of water that there is in the tank. Therefore, the water draining, or the rate at which it's draining, is going to get smaller and smaller and smaller. And eventually, when T gets to 40, because that's 40 minutes, your rate for the water flowing out should be 0, because again, you're almost done draining that tank. And again, we just want these applications for derivatives and how they work. And in the next section, we're going to be talking more about these applications and how we then start analyzing objects that move, and we then want to account for all of those changes. So for this topic, we are done, and stick around and we will be talking about related rates in the next video. I hope you all have a good day, and I will see you next time.